You guys, quiet down, please. Thank you. So a lot of documents you guys got. So the notes for today are right here. And we're going to go through these notes for most of the class today. Ms. York actually taught this class a G period, and I got to watch her do it. So I think I should do an okay job with you guys. Yeah, because she's the expert with series and sequences. So I'm following her lead. Because she's going to teach you guys next year too if you do BC. And she made these notes also. So we've been working in tandem because that way, when I hand you guys off to her, there's this nice smooth transition of, hey, she knows what you guys have done. She can help you guys move forward with this stuff down the road. The homework is also attached here. So if you have a little time at the end, you guys go ahead and start with homework. But today's notes are pretty lengthy. Now, just so you know, the other stuff that I gave you guys. Yes, I gave you guys 2 thick packets. Well, hold on. Just let me talk. Let me talk. All right.
Just hold on a minute.
Yes, you can. Yeah, you can read part of it. Okay. So if you look at these problems here.
I wonder who made this.
I got online somewhere last year. I found it random.
I think it was legal matter. I think
So there's 33 questions. Some of these questions are a little out of control. So what I did was last year, I made a list of these problems that there were. These 1 and 2 I thought were easy.
Medium hard.
Medium.
Don't worry.
Easier.
Don't worry.
Nine,
Hard,
whatever.
don't even touch
And
it.
if you're really feeling super ambitious, you could do those. Don't worry ones.
Oh, shit.
Now,
Impossible.
now to answer your question, Thomas, you can't read these. Yes and no. So, for example, the question's right here, right?
Okay.
So, like, here's one of the questions: 3 numbers A, B, and C in that order are given progression, common ratio, fine, whatever. Now, A, 2, B, and C are arithmetic progression. Return the positive values of R. So you have to, figure that B over A is R, C over B is R, 2B minus A is D, C minus 2D is also D, and do some sort of algebra to figure it all out, right? Now, each of these questions, the answer's right here. So the answer is provided for you. I want you to do the work. Now, how do you see the work? Now, yes, to your point, Thomas, you can't see that. You need a magnifying glass. However, what I've done is I posted this to Schoology. So when you want to look at the answers, go to Schoology, pull it up, and zoom in. Exactly. So if you zoom in, actually, I've not uploaded that one to online yet. So I will upload this later today. But you can actually look it up. So just so you know. These problems we'll talk about on Thursday. And we'll do it on Monday as well to review for the test. This is to expose you to as many hard series and sequence problems. Like not the ones that are calculus related that I've been doing with Ms. York with you guys, but more hey, just how do you handle hard series sequence problems? So to give you more exposure to that. That's what's going on there. Okay. This packet, we're definitely going to talk about on Thursday because we do need to review calculus because it's been a while since we've done some calculus work like derivatives and limits and whatnot. There's also one more topic of calculus I should talk about. Derivatives and exponential logarithmic functions. So we are going to do a lesson on Thursday. It's a little more calculus. This won't be on the test next week. This will be on the final. But I still want to get out of the way. So we're going to talk about it on Thursday. And it should be a short lesson. After this lesson, I decided to put like I don't have it queued up here, but in that packet, you'll see a bunch of old AP Calcs AB tests. This is when I didn't teach it this year, but it was a fall 2018. Ms. York and another teacher taught it, and I just put like an old test on limits, an old test on derivatives, an old test on derivative techniques. So you'll have that. So we'll talk about that on Thursday, and we'll talk about chain rule again, product rule, quotient rule, with exponential logarithmic functions as well. So you'll have a chance to review all that stuff because we need to talk about that, right? It's been a while since and a lot of people are gone Thursday anyway for AP World and what's going on Thursday. No one's in AP Stats in this class, but a lot of people will be gone for AP World that day. So I figure good for us to talk about. So, or if you do want to come to class because AP World's who's in AP World in this class? Okay, I mean you guys could come to class if you are you guys required to come to class? Okay, so I'll see you in class. Okay, but then I'll see you in class then. But here, okay, if you really want to use that time to say for AP World, I won't be offended. you could, but I'll see you. All right. Anyway, so let's get moving to the lesson, guys. Here we go. Let me pull up the fill-out notes from Ms. York, so I have them queued up here.
You don't do anything in English.
Okay, here we go. Okay, I can give my voice a little bit of break. Sean, can you read the objective, please?
Sure.
Yeah.
Objective. What is a power series? When do geometric or a power series converge or diverge? What is an interval of convergence and how do you find it for geometric power series? How can we express a geometric power series as a function and vice versa?
Okay, so when we think of a power series looks like this. We have a bunch of powers, right? What is a power? An expression has a base and an exponent, right? Like x squared is a power, right? The base is x, 2 is exponent, but the whole embodiment is called a power. And it's a series because you're adding up all these powers. That's really all it is. It's not nothing. It sounds kind of like cool, oh, power series. Just adding a bunch of powers. That's all it is. Nothing special. And then geometric, there is a geometric nature to it. Because if you think about it, what's the pattern you're seeing here? You're multiplying by what? X. Okay. So there's a geometric pattern to it. Okay. But then what would need to happen to have it converge? We'll talk about it. I think it's pretty obvious what we know about series and geometric patterns, but we'll talk about that in a moment. Interval of convergence, we'll talk about that. Like that's the range of values that X could be, so that the series will converge. We'll talk about that. How do we find from geometric power series, blah, blah, blah. And then how can we express geometric power series as a function? That's what we'll talk about at the end. But before we do that, let's introduce the power series. So below some examples, next to each one, determine the value of R. I write what is convergent or divergent. So for now, we're just looking at geometric series. They're infinite. So if you think about the first one, what is R here? I heard a 1/4. Okay, good. So 1/4. And would that converge or diverge? Converge, right? Because it's between -1 and 1. Good. How about the next one? -2/3. Converge or diverge?
Converge.
Converge.
Oh, converge.
Right? Because it's as long as it's between -1 and 1, non-inclusive. And how about for the third one? 3, and that diverges. Good. Okay. Now, if it does converge, let's find the sum. We should know how to do that. For the first one, it's 1 over, let me draw it better. 1 minus 1/4. Which should be 1 over 3/4. And 2/5. So it's 2/5 over 5/3. Flip it, and what do you get? You get 6 out of 25. Is that correct? Yeah. Which kind of makes sense. You know, 2/5 is 0.4, but you're subtracting, adding, subtracting, adding. So yeah. Okay, so that's just review. We're okay with that. Should be very straightforward. Okay, cool. Now, moving on. Okay, so now consider the following infinite series, which we're calling a power series, right? So in this case, it's still, this is still geometric, right? So compare the series to the ones above, how's it different or similar? Well, it's similar in the sense that it's still geometric. It's different compared to the second one. It's always going to start with 1 as the first term. So that's the one thing you do need to be aware of for infinite power series. And this is something you guys do talk about often in AP Calculus BC. So Ms. Yorkville is important that you guys get some exposure to it now, because it's a big discussion in AP Calc BC. Or, if you wind up doing more math later on and you do a class on series itself, some people take a class on just series, it's just something that's discussed. So you have some exposure to it now. So you start with 1 as the first term, okay? And of course, r equals x. We know this. So now, using that series, write the infinite series you get when you substitute the following values for x. Okay, so for example, if x is 3/4, how will my series look? 1 plus 9/16 plus 27 out of 64 plus dot, right? Okay. So what do we expect to happen here? It's generally going to look like plus 3/4 raised to the n power. Where we deliberately start with n equals what? Nope. Yeah, in this case, we're starting with n equals 0.
I thought you said always start with 1.
That's for that, right. No, I know what you're talking about, Thomas. You're talking about when we talk about like the explicit formulas for a geometric sequence. We start with n equals 1 for the first term. But like when we have summation notation, we could start it at n equals 0 if we wanted to, and have start at n equals 1. But I know what you're talking about some past stuff.
I just saw it start with 1 as the first.
Oh, got it. I understand now. Okay. Didn't know where the confusion was coming from. Okay, x equals 2. I think that's pretty obvious. 1 plus 2 plus 4 plus 8 plus dot, 2 to the n power. Again, we're assuming n equals 0 is the starting n value, right? So that's what we got there. And lastly, 1 minus 2/5 plus 4 out of 25 minus dot, And what are we doing repeatedly? Negative 2/5 raised to the n power, right? Okay, all makes sense? I'm cool with that. Great, awesome. Okay. So looking back, actually someone else can read. David, can you read? Look back.
Look back at the first 3 infinite geometric series from above. And any of them from the infinite series 1 plus x squared plus x cubed, blah, blah, blah.
Yeah, and so which of these 3 could do that? Clearly, the first and the third. Because the first one started at 1 and the third one started at 1. Not the second. The second one started at 2. So can I re-express this as an infinite power series? Yeah. I could let x be what? 1/4, right? Because I might multiply by 1/4 over and over again. And what would I let x equal here? X would equal 3, because r equals x, right? So I know it seemed like an obvious question, an easy question, but okay, so looking back at our answers above, give one of the value of x that when plugged into that will produce a convergent infinite geometric series and a divergent infinite. Because remember, x equals r, right? X is equal to the radius. So it's kind of open-ended. There's not like only one answer, but give me a possibility that x could equal to guarantee that this will converge. The sum will converge. 1/2, great. Give me an x value where it would not converge. 2, great. There we go.
Wouldn't it just be -1 greater than -1?
Exactly, right. Whereas here, you expect that to happen. Okay, now let's look a little deeper. Thomas, can you read the next part?
Say you're supposed to look at infinite series, 1 plus x squared plus x cubed and so on. This type of series that contains the variable x generates different infinite series depending on what you plug in for x. This is an example of a power series. A power series is an infinite series that contains the variable x that has a certain form, one for each value of x. We'll define it formally next year. A power series generates specific infinite series. This series is also geometric because there's a common ratio that will give the next term. Now we can call this series a geometric power series.
Yeah, and again, r equals x. We know this. So scroll down here. R equals x. So in order for infinite geometric series to converge, the absolute value r must be less than 1. So we expect the same thing for x. I already kind of wrote this already, but I'll write it again. Or you could write it like this. Which is kind of a little simpler. Or you could write it like this. I know, it's kind of weird. They don't know what this stands for? Good. I know, look at this guy. Elements, actually. E stands for elements. Elements. So this is set notation, actually. This is set notation. X is an element of 91 and 1. And why the parentheses, why not brackets? It's not included, of course. Yeah, exactly. Yeah. So the reason why I bring this up is that this notation could show up in calculus sometimes. So I don't want you guys to get confused. That just means element. Element means be a member of something, right? Like, for example, you have the elemental table. You know, like chlorine is a member of that table, right? Or oxygen is a member of that table, right? So whatever, right? Okay. So what we just defined right now is called the interval of convergence, which is abbreviated as IOC, not the International Olympic Committee. Dumb joke. IOC, interval of convergence. Okay. So this means what interval of values will force the issue of convergence. So it will make this converge. Clearly, when x between -1 and 1, we get convergence. But there could be different power series we could define. You'll see in a moment where the interval of convergence will be altered. We're going to see in the next example. The interval of convergence won't be from -1 to 1, will be something else based upon the transformation we're applying to the series itself. Okay. So let's move on to example 2. Consider the following power series. Okay, this is definitely a power series because what am I multiplying by? Well, sorry, it's a geometric. So before I say power, definitely it's geometric. What's my ratio here? 2x, correct. Good. And it's a power series because am I raising 2x to a power repeatedly? Yeah, 100% I am. Yeah, like what is it? What is this really doing? It's 1 plus 2x raised to the n power, right? Repeatedly. I mean, they did 2 to the n times x to the n. It's kind of nice to separate just to realize, like, x to the n, okay, 2 to the n, okay. But really, it's just 2 times x, the whole shebang raised to the n power, right? Okay. So now, let's figure out what would force the issue of convergence. I like 1/4. 1/4 is a great option for x. Why do you say 1/4?
2 times 1/4 is less than 1.
Yes, that's 1/2. I mean, there are other values I could have done. I could have done 1/3. Can I have done 2/3?
No.
No. What would happen if I did 2/3? That'd be yeah. Now we're not converging anymore, right? So I mean, of course you could go even bigger, but I would say I like to write 2/3 because 2/3 normally would if I didn't have the coefficient next to x. All right. If it's just 1x squared, x cubed, x 4, so forth, then great. We converge to 2/3. We can't, unfortunately, this. We cannot. But is this a geometric series? Yes, it is. And r is going to equal 2x, as I already said earlier, right? Now, find the interval of convergence. So in this case, we need absolute r to be less than 1, or the absolute value of what be less than 1? Correct. And now this requires a sign chart to solve. Either 2x is less than 1 or 2x is greater than what? Yeah. And actually, you know what? Let's consolidate it. Let's sandwich it in between those two numbers. Does that make sense? Right? Because you want R to be between -1 and 1. And then how would I isolate x in the middle? What would I do to both ends? Yeah. So that's your interval of convergence. And if you're asked to write interval notation, so yeah, we should get in the habit of doing that. You can write like this. Nah, I was just getting fancy on you guys. That's because Miss York had her notes, that's all. She is. All right. Okay. So we're good on that so far? All's good? No questions? Okay. So that's something that you will do often. And I'll tell you, interval convergence does get really tricky with trickier series down the road. But she at least wants you to think about, like, hear this topic now. So when she brings it up in a few months, you're like, okay, I know what it is. But then she's going to really give you some really crazy stuff. Ask anyone in BC, the eyes will bulge out of their heads when you talk about interval convergence, because there's some pretty wild problems. But for now, we'll keep it not wild. It's the first time we've seen it. Okay. It even drives me crazy when I see those problems. Okay, here's yet another power series. Okay, so we see some other things happening, right? I noticed that we're doing a transformation of 5 left, right? X plus 5, we know that's a transformation. So if you were to because we're going to express this as a function later on in these notes. But if you think about it, you're replacing x with x plus 5. That is a transformation, we know that. And also the bottom is now 3, right? So if you guys want to take a stab, what do you think R is going to be here repeatedly? Yep, that's where we're multiplying over and over again, x plus 5 over 3. Because if you think about it, if I raise that to the 0 power, that's 1. Raise it to the 1 power, I get x plus 5 over 3, and 2, and 3, and 4, and so forth. Now, if that's R, and so yes, this is a geometric power series. So if R is x plus 5 over 3, give me an x value that will force convergence. -6, let's go. Let's do it. Love it. -6. Because then R would be -1/3. Give me an R value that would not. 1, yes. Because then R is 2, that's a problem. We won't converge. So now find the interval of convergence. I'm just going to simply do this. Kind of keep it simple here. Just put in between -1 and 1 as a compound inequality. So just think about the algebra. What would I do algebraically if I said x in the middle? So if I multiply by 3 and subtract 5, I should get -8 and 2. -2, correct.
So it means that if there's an R value between -8 and -2, then it'll convert.
Correct. Well, x value. X value. X value.
Without R equals X.
Not in this case. Now equals x plus 5 over 3. Because that's what I multiply by repeatedly. Right? Multiply by that repeatedly. So the conclusion, guys, the interval convergence can be found by putting in the common ratio R into the inequality -1 less than R less than 1, where R equals R of x, where R is a function of x. So your goal here for these problems, express R as a function of x. Guys, quiet, please. Thank you. And that's what Ms. York is really interested in you guys seeing. Is how do you express a ratio as a function of x? Right? That's important. How to express a function of x? Because that's going to be a great strategy to help you find intervals of convergence for all these wacky things we'll do down the road. So we want to get in the habit of that. And of course, I said x afterwards. Again, all these other wacky tests, I need to brush up on because I forgot them. So if I do it for some for BC, then I have to refresh my memory, but I haven't done that in a while. Okay, so we're cool with that. All right. Okay, we're in the middle of notes here, we're doing great. Okay, I think you guys can handle this. Go and try example 4A and B. You could talk to somebody or ask me a question. I'm going to work it out also, and we'll compare it in a couple minutes.
You ever figure out zero factorial?
Not had time.
Oh, I looked it up. You looked it up on TikTok?
What did it tell you?
Really? You looked it up? Man, it's gone.
I'm sure when I see it, it'll make sense to me, but I just can't think on top of my head.
Why is zero factorial then? Because there's
Carry the
a
two,
factorial always ends in times one. Zero times one is zero. I don't understand. But you said zero factorial actually one. What? It's actually one. Yes. So I was like, why the hell? No, it's actually one. I was just like bugging him ever since I said, hey, it's three, you know, zero factorial. He's like, oh, pack it down. But like, what if we all agree that it's not one? People made up factorial. Alright, so how do we start? So can we change it? Can we petition to change it to make zero factorial?
Yeah, we can talk to the math conference,
Yeah.
the president of math. Yeah, or we guess Trump will do it for us. He would do that.
I don't understand. It's gotta be good. Because all I'm just gonna change it. Wait, is it? Yeah. Oh, wait, you have to flip this. I know because I don't get it. So that's crap. That's crappy. Okay, it's just backwards.
Okay, Thomas, we're gonna let AI Gemini answer this question for us. Yeah. That's what it says. Oh, okay, that's kind of interesting.
What does it say?
All right,
Like you can arrange zero objects in one way.
correct. Why? Yep. Yep, that's what it says. Yeah.
Yeah, negative x factor over two is the same as.
Right. Yeah. I didn't actually do the actual word. So it's.
All right, here we go, guys. Okay, so I start with the compound inequality, move between -1 and 1. Very important. If you multiply or divide by negative, you have to flip the inequalities. And the reason why you would do that is if you decide to move the variable to either end, you'd have to guarantee the same result. Like, for example, if you ever do like -2x plus 1 is less than 5, -2x is less than 4, x is greater than -2. That's because if I decide to move the 2x to the right side and the 5 to the left side, I have to guarantee the same result, which I would. That's why we always flip inequalities when we multiply and divide by negatives. And that's exactly what's happening for A and B. Excuse me. For B, we can't neglect -1/2 to the n power, because that is part of my r value. So my r is -1/2 times x minus 3. Solve for x, you should get 1 to 5. Okay, so we're okay with that? Okay, cool. Oh, another thing we should talk about too, which I see in the notes, but she didn't put in the question. We also want to answer the following: the center of the IOC. Yeah, exactly. So what would the center be for part A? Yeah, exactly.
What?
Where is the interval of convergence centered at?
Oh, the center of those.
Well, David, then now you're less confused. How about part B?
Yeah, 3.
3, there you go. And that actually matters a lot too. because when you start doing some other advanced series, I think Taylor series, if I'm not mistaken, you have to look at like the center and then make adjustments based upon that. Again, I'm rusty with the stuff, but it's something that I know you would need to do. Okay, we're at the home stretch here. Questions? We're okay? All right. Again, give my voice a little bit of a break here. Grace, you want to read the opening part, representations of functions? Okay.
Power series. To understand how a power series can represent a function, we'll go back and consider the most basic power series, the infinite geometric power series.
Okay, great. And I'll keep reading. So yeah, great. So that's what we're seeing here. So we know that the series will converge if x is trivial between a1 and 1, x is an element between a1 and 1, non-inclusive. We also know how to find the sum of the series if it converges. Remember, the sum of an infinite geometric series is defined as this, a1 over 1 minus r. But a1 is just going to be 1, and r is going to be x. So if you think about it, just related to what we already know. We know this because we got it from the we got it from the geometric series formula that was a1, 1 minus r raised to the n power over 1 minus r. And when r is tiny, 1 minus r is taken one away, we have this. So if I replace a1 with 1 and r with x, that's just gonna be 1 over 1 minus x. As long as x is between. So all this junk here, guys, all of this, believe it or not, adds to this, assuming that x is between a1 and 1, assuming that. So we can express this as a function. Or if you see this sigma notation here, where n equals 0 up to infinity of x to the n power, it can be rewritten like that. And we can actually verify this in the graphing calculator, by the way, guys. Let me show guys, quiet, please. Thank you. Yeah, you tell him, David.
I got you, Mr.
Yeah, I appreciate it.
X equals on.
Correct. Yes, correct. But look, let's just do this right here. Let me pull this up. So let's say x is 1/5. Okay. So if I were to do alpha window, x equals 0, and let's put a large number, say like 100, and let's do a power series. So if x is 1/5, then of course it's gonna be 1/5 to the x power. So alpha y equals 1. It's kind of nice. You could do it like this. Darn it, I kind of messed up here. Give me a sec here. Let me put another set of parentheses. Okay, now I'm really messing up. Okay, let's try this again. Alpha. Yeah, it's kind of dumb. I didn't make those questions. I'll tell you history behind it if you're curious, because I co-taught the person who wrote that.
Really? How the person that wrote the question?
Oh, sorry. That's X. My bad. You're right.
Are there extra one of these packets over there?
I thought I gave him one. No?
Yeah.
Okay.
Oh, okay.
So what's happening? It's the same thing as saying 1 over. I mean, it should be pretty obvious, I feel, but you're doing just this, right? Oh, hold on. What did I do wrong? Gosh darn it. Thank you. Yeah, same thing, right? So we can think of it like that. Okay. So now, guys, quiet. So now take a close look at the statement. You just create a relationship between a function and a series. So we now express a series as a function. Because 1 over 1 minus x, what kind of function do we call that? Rational, yes. We talked about rational already, right? You guys did it in Mr. Van's class, you did in this class, right? And if you think about that, that is definitely a rational function. with a vertical asymptote at x equals 1, horizontal asymptote at y equals 0. It has all the things that we expect of a rational function, right? And if we think about it, if x is between -1 and 1, and of course you have a vertical asymptote here. Yeah, if you were to plug in any of these numbers in for x, right? Excuse me. Yeah, if I were plugging like say -1 for x, what would my ratio be here? Or sorry, what would my sum be? Sorry, my sum would be 1/2, right? And of course, if I were plugging any of these other values, I'll get other sum values. If I plug -1 in for x,
So that's the sum expressed.
correct. Yes. Yeah. So
But then,
It's always exactly the same sum.
yeah, shouldn't you like cut the graph off after 1 and -1?
well, hold on one sec, actually. Let's do the partial sums because give me one sec here. Okay. So if I plug in 1, well, hold on. Give me one sec here. Actually, now I'm a little lost with these notes. Give me one sec. Let's just move on to example 5 because I'm not sure what I'm just know just know you have a graph there. Okay. Well,
So it's okay if we don't understand a single bit of this graph.
we know this. Okay. You guys know what's going on with the graph, right?
No.
What?
Why do you say?
How do you not know? Just a rational function. That's all I'm doing. Yeah, that's all I'm doing, right? Okay.
Well, why? I feel like I've seen this graph before.
Yes.
But
Yeah.
why? What is it telling me?
Yeah.
Okay. Let me get back to you on that.
Okay.
Okay, I'll get back to you on that. Okay.
I know on the graph one of the.
Let me get back to you on that. Okay. Well, here's a.
Right when you get back to Gemini's cooking it up.
Actually, I already forgot the factorial one. Yeah. There's only one way to arrange a number 0. Because the factorial comes from a permutation, right?
Oh, factorial.
Okay, but okay, so for example, there's 4 of you guys, right?
No.
How many ways can I arrange you guys in your chairs? There'd be 24 ways.
Yeah.
Because that chair had 4 options.
Yeah.
I put David, Thomas, Grace, or Jackson in that chair.
Yeah.
Right? I have 3 options for that one. Then 2, 1. So 4, 3, 2, 1. So that's 4 factorial. 3 factorial would be 6. 2 factorial would be 2. 1 factorial is only, there's only one way I could arrange one, but let's say all of you guys leave. Okay, well, how many ways can I arrange nobody in that chair? Well, just one way.
Or infinite.
And that's why it's 1.
But that is 0. You have different.
That's why.
But there's nobody. There's not even a chair.
No, there's a chair, there's nobody in it.
Well, now we're getting very philosophical. Okay. Okay, guys, quiet, please. Okay, so anyway, I think the bottom line is this. Make sure you're comfortable. Sorry that I'm botching these guys, I gotta finish this up. Thank you. I know I kind of botched this little part of the notes, but here's the thing. 1/1 minus x, that's a sum. We're okay with that, right? Because your first term is 1, your ratio is x. And how do I find the sum of infinite series? A1 over 1 minus r, right?
Yep.
So again, A1 is 1, r is x. Now, can they be expressed graphically? Sure. That's all we see there. We see a graph. That totally makes sense. From this relation, we can create other relations between functions like this to other power series similar to the one above. Now, if you want to take a deeper look at this function, we can. Can you factor a negative from the bottom and make it look like this? Sure, right? And if you think about 1 over x, how does the graph 1 over x look? Like that, right? Do you agree? Okay. What does the negative do to this graph?
What's it?
Was the plus one do? It shifts it, right,
Yeah.
exactly. So, so that's what we're seeing here. So, but anyway, let's just move on to example 5.
Oh, I get it.
Okay. So what you want to do next is this one here. Think of this as 1 over 1 minus negative x. So that becomes your r value. R becomes negative x. So the power series looks like this.
So it's gonna okay, so it's gonna alternate back and forth. between-
So
One because of negative x to 0.
correct.
Minus x cubed plus x to the 4.
And of course, my interval of convergence still has to be between -1 and 1.
Well, why do you rewrite it into minus minus x?
So do we,
So because in order to so what we're trying to do is we're trying to compare this sum of an infinite series, infinite geometric series, which is a1 over 1 minus r. But because it's a power series, we know a1's 1 anyway. So we're cool. We got 1 up top. But then you have to make this as 1 minus r. So compare 1 plus x to 1 minus r. If you compare 1 plus x to 1 minus r, what does r have to equal? So you compare this. I probably should start with that. Compare with 1 minus r. So clearly r has to equal negative x. So if you wrote a general function for it, for each term, it could look like this. That's how every term generated. So essentially all this junk, you see this, all this junk equals 1 plus x. So if someone showed you a series, 1 minus x plus x squared minus x cubed plus x4, whatever, right? That equals 1 plus x. Cool. Let's move on. Last page. Example 5. B. Okay. So just to kind of make things easy for ourselves, we're going to compare 1 minus r. So is r equal here? Or in this case, 1 minus r equals x. So what's r going to equal here?
1 minus x.
1 minus x. Actually, wait 1 sec.
yeah,
Yeah, that's correct.
Didn't trust you. Mister, you didn't trust me until Sean confirmed it.
No, I was looking at the notes. Sorry. No, please don't take offense to that. Okay. For this one's kind of interesting, but let's finish off these right here. Okay, so if r equals 2x, then we know this to be true, right? Okay, Dave, why don't you tell us the answer to that? I trust you.
Oh, the answer.
Yeah,
What is that?
for part B.
That's an arrow. The point, part B. Negative 1/2 is less than x is less than 1/2.
Correct.
The
Yeah.
reason that's asked Sean.
Okay, well, let Sean do the next one. All right. Okay.
You probably can't figure it out.
And by the way, the center is 0. Okay.
Do we need to say the sentence?
No, I just felt like it. Okay. So for part C, you could also write like this, by the way. Because what's happening is that when we write the sequence, it's going to look like this. Well, so you can see the power series, that's why. So, because they're always multiplying by a negative x, but I mean, it's 1 minus x, obviously. So your interval, but your interval is going to be
R equals 1 minus x or negative x.
correct, right? So when you find the interval of convergence, that could be pretty loud too. Anyway, from 0 to 2. I know we're in Miss York right now. So your interval convergence from 0 to 2, the center would be 1, by the way. What was the center? What? Just you'll see next year. It's more of just terminology that we're getting through. Okay. Any questions about B and C before I do D? Okay.
How does like showing yourself the series make it easier to solve?
That's not making yourself. We're just trying to show that this is a power series.
Okay.
Actually, we're actually being asked to find the power series. So we are being asked to do that. I just didn't do that for part B, but
Okay.
for part B, the power series, by the way, because R is 2x, it's gonna be 1 plus 2x plus 4x squared plus dot plus 2x raised to the n power. Yeah, I wasn't really answering the question, so okay. Okay, guys, ready for part D? Okay, part D, here we go. We'll go green, change up a little bit. Okay, I would take out the x and write it like this. Okay. Does that make sense what I'm doing so far? Oh wow, she's upset. Okay, everyone's like yelling today. What's going on, man? It's all stressed out. Okay, we just love math, man. I don't know.
Guys, understand the graph.
Yeah, you tell them. Okay. By the way, what's your R value here? X. So when you write the power series is going to look like this, guys.
Like there's gonna be extra wire.
Yeah, you're going to put X on the outside. And it's 1 minus X Okay. So first of all, interval convergence is still -1 to 1. That didn't change one bit. So the IOC the center is still 0. You guys don't know the relevance behind it, but who cares? Okay. But here's the thing. The power series always starts at 1, and you're multiplying your R is negative X. We're going to be multiplying negative X repeatedly. So 1 negative X plus X squared. But one little twist is that you have an X on the outside.
Let's say -1 and 1 as they are, I assume.
Correct. Yeah. So if I put the X inside, truly my power series starts to look like this now. But I'll erase the top because I'm running out of space here. Okay. So really, it's like saying x minus x squared plus x cubed minus x4 plus dot dot dot. So if you see a power series like this, don't worry. Oh, it doesn't start at 1. Factor out the x. Make it start 1. And then we express the sum. You recognize, okay, r is negative x. I do 1 over 1 minus negative x. Oh, but times x on the outside. So so this could be a test question, by the way. This could be a test question. I could say, here is a power series. Express this as a function for me, please. And then what you would do is you'd write that. Why does that make sense? Because you factor out the x. You notice the geometric pattern, which starts at 1. And what's the ratio again? After you factor out the x, the ratio is negative x. And how do you find the sum of infinite geometric series? A1 over 1 minus r. Your A1 is 1. And your r is negative x, and you have it. Or you can just look at like the way it looks right now. This is still an infinite geometric series. What's your first value here? X. What's your ratio? So you can also just think of it as x over 1 plus x, right? Exactly. Okay, I've got 2 minutes left. Okay. Don't know if I'll quite get to this. Let's look at 7. Find integral convergence of all that junk there. Yeah.
Pull the one, like, can you pull constants in front of the?
Yeah, yeah, yep, yep. Okay, so what's my r value here?
4.
Not quite. Okay, if n is 0, what's my first value, guys? 1/4. Very good. Now, if n is 1, what's my second term? So x minus 1.
Over -4.
Correct. So if you think about it, what am I multiplying by repeatedly? Well, 1/4 is my first term. Yes, thank you. 1 minus x or negative parentheses x minus 1. Either way is fine. So the sum, if you clean it up, be 1/4 over 1 plus x. There's a lot of negatives, but it's actually minus 1. So what does it converge to? 1 over 4x. It's really tricky. Top on negative here. Negative and negative was positive 1, but 1 minus 1 goes away. Get 1/4 of x is 1 over 4x.
1 minus 1.
Okay. Sorry I didn't get to example 6. I'll do that on Thursday with you guys. Cool. I think we're all set.